Your brain's response to stress isn't just emotional, it's structural. Within weeks, chronic stress can reduce dendritic branching in the hippocampus, the brain region responsible for memory formation. This contradicts the common belief that stress only affects you mentally or emotionally. Researchers at Yale found that chronic stress can lead to a reduction in gray matter, impacting cognitive processing. Far from being just a bad day, stress reshapes neural architecture at a cellular level. This means your capacity for memory and decision-making can be physically altered. The process isn't just metaphorical, it's measurable and visible under brain imaging technologies. The amygdala, your brain's fear center, becomes hyperactive under stress. But the real kicker, this hyperactivity increases connectivity with the prefrontal cortex, the very area responsible for rational thinking and decision-making. In a study of 100 participants by Stanford University, heightened stress led to 20% more connectivity between these regions, muddying emotional and logical responses. This increased connectivity isn't just transient, it rewires how you process fear and logic, blending them in a complicated neural dance. While stress is often seen as a temporary state, these changes can last far beyond the stressful period. Hyperactivation isn't just emotional, it rewires your neural pathways. Cortisol, the stress hormone, is notorious for its effects on the body, but its impact on the brain is equally profound. High cortisol levels lead to a thinning of the prefrontal cortex, impairing your ability to focus and plan. This isn't a vague claim. MRI scans show a 14% reduction in thickness among individuals with prolonged stress exposure, according to Harvard Medical School's research. Cortisol's influence extends to the hippocampus, where it impairs its ability to generate new neurons. Your brain's capacity for adaptation and learning is compromised at a cellular level. This is a physical transformation, not just a mental strain. Dopamine, the neurotransmitter of reward and pleasure, is another victim of chronic stress. Prolonged stress leads to dopamine receptor downregulation, reducing your capacity for experiencing pleasure. A 2017 study in the journal Nature Neuroscience observed a 30% decrease in dopamine receptors in participants under chronic stress. This isn't just about feeling down. It's a biochemical reality affecting your motivation and engagement with life. The downregulation isn't simply an emotional reaction. It's a tangible alteration in how your brain's reward system functions. This shift makes everyday pleasures feel less rewarding, altering your baseline mood and motivation profoundly. It's easy to think of habits as merely behavioral, but stress reveals a deeper truth. Chronic stress activates the basal ganglia, embedding stress-related behaviors into your neural circuitry. The University of Cambridge found that stress-induced habits can become ingrained, with changes observable on fMRI. This activation encodes habits into a physical loop, making them harder to break. It's not just willpower, it's a brain circuit hardwired by stress. The basal ganglia's role in habit formation means stress doesn't just affect mood, it changes how your brain encodes behaviors. These habits become a part of your neural architecture. Chronic stress triggers cortisol release, affecting hippocampal dendrite density. Cortisol binds to receptors in the hippocampus, leading to dendritic retraction. This process reduces the complexity of neural connections, impairing memory formation and recall. In a controlled study with 50 participants, increased cortisol levels resulted in a 20% reduction in dendritic branching within just 2 weeks. These changes are not just transient. Prolonged stress can lead to permanent structural damage. Dendritic retraction compromises the hippocampus's ability to integrate information, affecting both short and long-term memory. The impact is cellular, but has profound effects on cognitive capabilities. Stress-induced amygdala hyperactivation isn't just about feeling anxious. This hyperactivation strengthens its connections with the prefrontal cortex, altering emotional response and decision-making. Increased synaptic activity between these regions changes response patterns, making fear-based decisions more prevalent. A 2015 study published in the Journal of Neuroscience found a 25% increase in synaptic strength between the amygdala and prefrontal cortex under chronic stress. This isn't just a passing effect. It rewires the brain's circuitry, prioritizing fear responses over rational thought. This synaptic strengthening is a physiological adaptation, embedding stress responses into the neural network. Under chronic stress, the brain's reward system takes a hit through dopamine receptor downregulation. Stress reduces the number of dopamine receptors in key areas like the nucleus accumbens, diminishing pleasure and motivation. This downregulation, observed in a study by the University of Michigan involving 60 subjects, showed a 35% decrease in dopamine receptor availability after a month of stress exposure. These biochemical changes cause everyday activities to feel less rewarding and can lead to anhedonia, a lack of pleasure in previously enjoyable activities. It's not just feeling demotivated, it's a neurochemical shift that alters perception. The basal ganglia, a brain region key to habit formation, becomes more active under stress. This heightened activity facilitates the encoding of stress-related habits, embedding them into your neural circuitry. Functional MRI studies by MIT researchers have shown a 30% increase in basal ganglia activity under stress, leading to persistent behavioral patterns. This isn't merely a psychological phenomenon. It's a physiological encoding of habits into brain structure. The basal ganglia's role in habit formation means stress not only affects mood but also how behaviors are hardwired, making them difficult to change. These neural pathways become entrenched, altering behavior long-term. Stress affects the brain's default mode network, DMN, a system active during rest and introspection. Chronic stress disrupts DMN connectivity, affecting thought patterns and self-reflection. A 2019 study involving 80 participants showed decreased connectivity in the DMN under prolonged stress, altering how the brain processes internal thoughts. This disruption isn't just abstract. It has a measurable effect on attention and creativity. The DMN's altered activity changes how you perceive and engage with your internal world, affecting everything from daydreaming to problem-solving abilities. Stress reshapes not just external responses, but internal mental landscapes. Chronic stress differs from acute stress by its lingering effects on the brain. While acute stress might temporarily heighten alertness, chronic stress leads to sustained cortisol release, eroding hippocampal volume over time. A longitudinal study by the University of California followed 100 individuals over 5 years, finding a 12% decrease in hippocampal volume among those with chronic stress. This reduction isn't reversible simply with rest. It represents a structural alteration. Unlike the short-term boost of acute stress, chronic stress leaves a lasting scar on the brain's landscape, influencing memory, learning, and emotional resilience in a way that persists well beyond the stressor's removal. Self-help narratives often oversimplify stress management, but peer-reviewed neuroscience reveals complex realities. For example, while mindfulness is often touted as a panacea, MRI studies show that structural changes in the brain require consistent practice over months, not days. A 2018 study showed that 8 weeks of mindfulness training increased gray matter density, but these changes were modest compared to the rapid, pronounced effects of stress. Brain imaging illustrates that stress can rapidly alter brain regions like the amygdala, whereas positive practices require sustained effort to induce similar changes. The brain doesn't easily rebalance. It demands ongoing, deliberate engagement to counteract stress. Brain imaging studies offer a stark contrast to popular psychology claims. Functional MRI shows that chronic stress can reduce prefrontal cortex activity, impairing decision-making and impulse control. This is not a transient state. A 2020 meta-analysis found consistent reductions in prefrontal activity across multiple studies involving over 500 participants. This neural suppression isn't easily mitigated by positive thinking or short-term interventions. The brain's response to stress is both profound and enduring, reshaping the neural pathways that govern critical executive functions. Long-term stress management strategies must consider these underlying neural changes, rather than relying solely on surface-level psychological approaches. Chronic stress contributes to synaptic pruning, especially during adolescence. This process, meant to streamline neural networks, can become excessive under stress, leading to a loss of crucial synapses. A 2016 study in Nature demonstrated that stress accelerates synaptic pruning in adolescent brains, potentially affecting cognitive development. This is significant because adolescence is a crucial period for neural growth and adaptation. Overactive pruning under stress can disrupt the balance, affecting learning, memory, and emotional regulation. The effects aren't just immediate. They can shape the brain's architecture into adulthood, setting a trajectory for future mental health challenges and cognitive limitations. A striking study in 2019 revealed that the impact of chronic stress on brain volume can be quantified. Using MRI, researchers found that individuals with high stress levels showed a 5% reduction in overall brain volume, particularly in areas related to emotional regulation. This isn't merely a psychological state, it's a measurable change in brain structure. The study involved over 1,000 participants and underscored the long-term physical impact of stress beyond immediate symptoms. Understanding these structural changes reframes stress as not just an emotional burden, but a physiological condition with lasting implications, emphasizing the need for effective, targeted stress management strategies.